Hi everyone, welcome back to my channel Embedded Mindset. Previously we have seen how to use the GPIO pins, how to configure them as an input-output pin. We have toggled the LED and we have seen how to configure the output pin, and we have connected the switch and made to work it in both the triggers, that is state trigger and the level trigger. Today we are going to concentrate on the next topic, that is the timer. We can see the timer is timers and the watchdog. Timer is a hardware peripheral inside the microcontroller. How it works means, just think of them like a digital stopwatch. They count clock pulses and can perform an action when a specific timer or a count is reached. In this, we have multiple timers like advanced counter timer is often a timer 1. General purpose timers we have 4, timer 2, timer 3, timer 15, timer 16, and there is a basic timer 6. Here's a description. These are the 16 counter resolutions, counter types, whether they are up counter, down counter, or up down counters, and the prescale factor, DMA, request generation, capture and comparison. This is a description of it. Now, today we are going to concentrate on advanced timer 1. In timers, we can see the working of two multiples, that is external crystal clock and the internal crystal clock. For the external clock, here you can see that a clock source where it is of 4 to 48 mega crystal oscillator and 32 kilohertz crystal oscillator for RTC, and there are some internal clock oscillators. The internal oscillators are HSI16, low power crystal oscillators, multi-speed internal oscillators, and HSI48 megahertz crystal oscillator. So depending on the application, we can select one of the clock sources. For our example, we will use the internal 16 megahertz HSI clock for today. For the today, I have told there are 4 internal clocks. Today we are going to use HSI16 high speed internal 16 megahertz oscillator clock. Now let us see how to configure this HSI16 internal clock of 16 megahertz, and then how to select the timer 1, how to configure them and utilize it. Here this is just a basic function where I have declared a LED of GPIO A to use in the further in the example. Now for the configuration, let's first initialize the timer. Now what we need to do in the first step is we need to enable the HSI16, which makes the 16 megahertz clock oscillator to work with us. For that, what we need to refer is the manual data page of the STM, where we need to find the RCC register that is available at RCC register, that is clock control register, RCCCR. Here we can see there are multiple internal clock which we have to configure. We are using HSI16. So before configuring the timer, we need to make sure our system clock is properly set. So in this code, we are using HSI16 clock. So first we need to configure the HSI on this 8th bit. We need to do is, if it is 0, it means the HSI oscillator is off. 1 means HSI oscillator is on. So let us enable this register pin first. CR that is HSI on, which means enable the HSI16 clock. Next, in the clock, when you enable the clock, after enabling the clock, there will be a slight delay to fetch the hardware. So for that, what we need to check is, we need to check the status of the register pin, whether it is ready or not. So for that, what I need to do is, there is a register called HSI ready in the 10th bit. If it is 0, then the HSI oscillator is not ready. If it is 1, the HSI oscillator is ready. I need to wait until the oscillator changes its states from 0 to 1. So to check that, what we do is, we will wait in a loop that RCC CR. I will make a AND operation with the register. What will this do is, this will do an AND operation with this register bit of ready, whether it is a 1 or a 0. Sorry, AND operation with the complete register pin. If this is 1 and it does the operation of 1 with this bit, then if it is 0, then not ready. 1 means ready. But now I need to check if it is 0, then the loop comes out. The condition to make this is top like this. This is equals to what is while this operation is equals to 0. If it is 0, then it stays in this loop. When it becomes 1, it gets out of the loop. It means the HSI16 clock is now ready to use. Now I have enabled the pin. Next, I need to configure the HSI pin. For the configuration, I need to go to the register called clock configuration register. Clock configuration register. The system clock is that drives the CPU and the peripheral. First, here you can see I'm concentrating on HSI16. Where I can find that is first hit the 0 and the 1 bit, the system clock switch. HSI16 selected for the system clock. For this system clock, I need to make the bit 1 and 0 to 0 and 1. As we have seen, we need to make HSI16 as 0 and 1. For that, what I will do is, first I need to clear this 2-bit and then set this to 0 and 1. For that, first to clear RCC, this CFGR equals to, I can use directly the user defined library function and call like this. This will make the bit clear. Now to set that HSI bit, I can write R or with RCC CFGR SW HSI. This will clear the SW bits first, then sets the HSI 16 megahertz clock. Next, after this, what happens is this sets the SW bit to use the HSI16 as the system clock. So now the entire microcontroller, including the TIMER1, will run from the 16 megahertz internal oscillator. So now effectively this line says that starts the 16 megahertz internal clock. Now we need to wait until the clock is ready. Just enabling the clock is not enough. We must wait until the oscillator has stabilized. That what we can do is in the same register, here we have SWS system clock switch status, whether it has been switched or not, to check the status. For that, HSI16 oscillator used as a system clock. If it is 01, it means that the system clock is ready to use now. For that, I need to read 0 and 1 from this SWS bit. To read that, we are writing the function again while RCC CFGR and with RCC CFGR underscore SWS. This operation will check the present state of that SWS bit, and that should not be equal to what this line states is, we know that when the HSISWS bits become ready, it will be 0, 1. So until this bit gets equals to, like suppose this is 1, 0, and we know the HSI should be 0, 1. Until this operation becomes equals to 0, 1, this loop will run in this while loop. After both are equal, then it gets out of the loop, so that we can say that the system clock switch status which we are utilizing, it is ready to use. Always remember, don't move forward until the system clock is confirmed to be as HSI16 is working. Now just a small recap, what we have done is we have enabled the HSI internal clock. Until it gets stable, we have run the loop. After it gets stabled, we come for the select the HSI16 system clock. We made it to the operate and the bit of SW201, and again we have waited until the switch is confirmed. Next, what we do using TIMER1, we first need to enable its clock. In STM32, peripherals are connected to different buses, but the TIMER1 is on the APB2 buses. So first we need to enable the TIMER1. Here you can see APB2 peripheral clock enable register. In this we can see there is a, in the 11th bit, TIMER1 enable. So 11th bit, we need to make this to enable. For that, RCC APB2 ENR, RCC APB2 ENR, we will set the bit APB2 ENR underscore timer1 enable. What will make this is this will enable the timer1. Next, here is the timer1 functional description. This is one of the main important topic to configure the timer 1 now. This timer 1 unit is a programmable advanced control timer. It is of a 16-bit counter with its related auto reloader registers. It can up count, down count, or both up and down. The counter clock can be divided by the prescale. The four basic unit this includes its counter register, prescale register, auto reload register, and the reception counter register. The main important two things which we are going to use today is prescale register and the auto reload register to configure the timer 1. For what purpose the prescale we need is, suppose this is in a 16 megahertz I have been configuring. So a 16 million ticks per second is way too fast to work with us. So by prescaling we can divide that and slow down this clock down to the more manageable speed. From that we can use it easily. For this prescale, here are the configurations which you can see and understand. The counter timer diagram with the prescale divisions has been changed from 1 to 2. Here you can see the differences in the timer clocks when it has been changed from 1 to 2 and 1 to 4. This is one of the example pattern how it gets changed. The prescale counter formula for this prescale counter is, we can see in the description also, like the timer 1 prescale which comes under these four registers. Here you can see the timer 1 prescale is of a 16-bit TSC. It is been denoted as, here you can see the counter clock frequency CKCNT is equals to FCK underscore PSC whole divided by the prescale. Now we need to configure for this prescale by the formula which we have read. CKCNT equals to FCK underscore PSC divided by PSC 15 plus 1. Let's interchange them, and we wanted the formula for PSC 15. For the PSC 15, bring this to the top order and reload it. Change, we get the formula as FCK PSC divided by CKCNT whole minus 1. Now in this, FCK underscore PSC means the clock which we are going to use. In this FCK is the frequency which we have selected, and CKCNT. This can be assumed by us, and we, we know that the PSC is a 16-bit. It means the maximum value which PSC can hold is 65536. So configure select this CKCNT in such a way that you also get the proper round figures, like this is a 20,000 and by minus 1 it is 19999. This PSC should be below the 65536. Don't exceed this value and configure it. And here let's configure the timer1 prescale equals to 79 19999. We have configured. Now let's move to auto reload register. This register holds the value that the timer will count up to. The timer counter starts at 0 and starts incrementing every tick for the new events. So, and there is an update event called when the counter reaches the value in the auto reload register that will roll over to 0 and it generate updated event, and we configure this event to trigger an interrupt now. So in this auto reload register and the update event, there will be a overflow in the auto reload. So the overflow frequency is equals to speed of counter clock divided by auto reload plus 1, and for the update event frequency equals to counter clock speed divided by ARR plus 1. So we will do for this update event frequency. This is nothing but the interrupt handling which we are going to see now. This counter clock speed can be configured as peripheral clock divided by PSC plus 1. This is just the derivation for it. The update frequency of update peripheral clock divided by, where we know the frequency is 1 divided by T. So the peripheral clock is configured here. We need to calculate for the auto reload. So the auto reload formula will be FCK into T divided by PSC plus 1 whole divided minus 1. Now FCK is nothing but the clock frequency which we have selected, that is 16 megahertz, and T is nothing but the time interval which we want to calculate. Suppose if you want to calculate for every 1 second, take 1 second, 0.5 millisecond, you consider here 0.5, for 5 seconds consider 5, so on, whole divided by the prescale which we have calculated before, 19999 plus 1, which gives you the ARR equals to 799. This is the derivation for auto reload. So now let's configure this also. Time 1 ARR to 799. Now we have configured the prescale and the auto reload. As we understood that after the timer 1 auto reload, it reaches its value, again it generates an interrupt and set back to 0. So now when it generates an interrupt, so now we need to enable the interrupt. So instead of checking the timer manually, we can use this interrupt to let the microcontroller notify us when the timer is overflow. So we enable update interrupt like here you can see we have a timer DMA slash interrupt enable register. There are more configurations in this like timer DMA, com DMA request. We have capture set comparisons 2, 3, 4 lot. But what I need to do is I need to just enable the interrupt for my timer. So that is update interrupt enable 0 to disable and 1 to enable. This is enough for me. So I will just enable this 1 bit is enough. For that, timer 1 represents as DIER. DIER enable the bit timer 1. This will enable my timer interrupt. So then we start the timer. Now let's go for the other register called timer 1 control register. Timer 1 control register. We need to concentrate on register 1. Timer 1 CR1. Yes. Here what we need to do is we need to enable the counter pin, that is enable this counter enable. So we need to set this bit to 1. For that, time 1 CR1 or with time underscore CR1 CEN. This will enable my counter pin. Now finally we need to enable the interrupt and we need to call the ISR module. To enable the interrupt, we can call we have an NVIC function, that is IC enable IRQ time 1 up counter of 6 IRQ enable. This is the function which will enable the interrupt service routine ISR and call the function. We'll call the ISR function now. That will be of would time 1 counter or 16 IRQ handler. This will handle my interrupt IRQ now. What we need to do in this is we need to check for the interrupt occurrence. So to check that interrupt occurrence, we can see in the register called TIMER1 status register. In this, the bit 0 update interrupt flag. So as I told you, when the ARR starts, the counter starts counting from 0 to 799. After 799, it creates an interrupt. That interrupt will be reflected in the ISR handler. Here, when the interrupt occurs, this bit UIF will automatically set to 1, which represents for us that interrupt has been occurred in the register pin after 1 second, because we have configured our prescale and auto reloader based on per second now. So we need to check the interrupt. If TIMER1 SR and with the score SR score UART, if it is detected, means TIMER1 interrupt has been occurred. At that time, what I can do is, first I will make this pin again to set to 0, because I need this interrupt to occur frequently. It should not stop. Based on the time which I will configure, the interrupt it should be occurring for me. Now what I will, in this init configure, you also call the function init TIMER1 TIMER1. Yeah, Now let's declare one, that is volatile unsigned int 1. I have declared this globally unsigned int 1 second. What I will do with this is every time when for 1 second this interrupt will occur, at that time I will also increase my this 1 second, like 1 second will be incremented. Now the reason why I have configured this LED pin is to check for every second the LED gets toggled. Before, you know that we have used just the blocking delay, but now in the main function, while one, what we will call if 1 second equals to 1, at that time LED will toggle. Now I will tell you what happens. Every 1 second the interrupt will be occurred. This interrupt will be checked and this will be made to back to 0, or else this loop always it will be a true one. So there should be a gap for a second. So for every 1 second the interrupt will be occurred and this 1 second will count. Now when in the loop every 1 second is equals to 1 means every 1 second when the interrupt is occurred, the LED will get turned on for 1 second, and again the 1 second will be 0. At that time this loop will not be incremented because the interrupt will be also 0. When again the interrupt occurs, the 1 second will increment by 1, and in the loop 1 second will reach to 1 second. This gets true and the LED will get toggled again. Now if I want to toggle my LED for every 2 seconds, 3 seconds, 4 seconds, any of the second, what I need to do is just I need to increment this for every 2 seconds, 5 seconds, 10 seconds. Okay, now if I do for a 2 second, what happens? Let's see. Initially the 1 second will be 0. At the time 0, this will not execute. The LED interrupt will occur. The interrupt will reduce to 0 again. The the 1 second will increment by 1 first. This condition, if 1 equals to 2, this gets false because it is now 1. So this will not execute. Again it will wait for 1 second. When the interrupt occurs again, At that time 1 second will be incremented from 1 to 2. That time 1 second condition equals to gets true, the LED will toggle. Let's configure this and check how the timer is working. Let's debug this. Okay, the error is I'm using the pointer. Okay, okay, let's go connect our STM and run the code. Yeah, the code is running properly. At the last I will share the video of LED how it is toggling for every 2 seconds. By that you can confirm that how the program is running accurately. Once you can check the program completely, and thanks for watching my video. For more upcoming topics advanced in STM32, please follow my channel and like, share and subscribe. Thank you.